Welcome back to the lecture on drone systems and control. In a previous lecture on control systems, the module of control systems, we have gone through a lecture on PID control, right. We have focused on the idea of proportional integral and derivative control separately, but that was a more generic lecture, though we have presented one example of drone altitude control. In this particular lecture, we will be focusing on another aspect of PID control, that is called trajectory tracking. Okay. What do we mean by that? We will see in this lecture. We will talk about the role of PID control. We will focus on like the PID control principles separately for trajectory tracking. Then we will see control loop, nested control loop for drones. We will talk about inner loop and outer loop. We will see what are the roles of two different control loops for drone navigation and control, and we will give some examples, indicative examples, which will help you understanding that how PID controller can be designed for trajectory tracking purpose. Okay, fine. So, what is tracking control? For tracking control, the goal is to ensure that a system's output follows or tracks a given time varying reference signal. Okay. What is a time varying reference signal? It can be trajectory also, trajectory of the drone, which varies when the drone is moving. The trajectory is also varying with time. If there is a predefined trajectory for the drone, then the drone needs to track the trajectory to reach from its source point to the goal location, right. So, the trajectory should be followed or tracked as closely as possible. Okay. So, for that, if we just expect that the drone will by itself track the trajectory, it does not happen all the time, because there will be some errors in the system. The plant or the drone might sometimes behave in a little different way. There can be sensor errors, there can be external disturbances like wind, gust, noise, etc., sensor noise specifically. So, we need to design a control law that minimize the error between a desired reference trajectory and the actual output of the system over time. What does that mean? If we are specifying that in a 2D plane, the drone should move in a straight line, okay, then the drone should follow the predefined trajectory as close as possible. There might be some variations, but it should be able to follow this trajectory as soon as possible, right. If there is some obstacle in between where the drone cannot go through the obstacles, then it should avoid the obstacles by some other means of avoidance algorithm, and then again should come back to the main trajectory to reach the goal location, and this point is the source. Okay, fine. The example in drone context can be given in this way. A drone is given a circular path to fly. Okay. So, the drone should be following a circular path for what? Maybe for any surveillance purpose. There is some disaster affected area or some important zone which autonomously we want to monitor, and we want to use a drone for that. Then the drone is moving in a circular path to do the surveillance, and then what is the expectation? For tracking, it is expected that the drone with minimum variation of the predefined trajectory, minimum deviation from the predefined trajectory, should keep on doing the surveillance properly. Okay. So, the actual trajectory is the drone moves in real time. That means, in this particular plot, the blue one which I have drawn before was the reference trajectory which was given to the drone to follow, and the actual trajectory of the drone should be as close as possible to the reference trajectory. Okay. So, we talk about actual trajectory as well. Now, what is the error? Tracking control ensures that the drone continuously adjusts its thrust and orientation to reduce any deviation from this path. Okay. Now, you understand what is the deviation? The reference trajectory is something which is already given, but in actual, when the drone is trying to follow it, there might be some tracking error. Okay. So, that error is represented by this equation, where the error ET is equal to reference minus the actual output. Okay. This particular expression we have gone through many times in this lecture series. So now you know what is a reference signal and what is the actual signal, and what is the objective. We want to keep the error, that means the difference between RT and YT, as minimum as possible. Okay. So we want to design a control input UT such that this particular error goes to 0 as t tends to infinity. However, we can't wait till infinite time, because that will be a question on the speed of the system. We need to reach the target trajectory which we need to follow, a reference trajectory, as soon as possible. So, for that the error should be going to 0, okay, in some finite time. Fine. So, the drone is required to follow a predefined time dependent path in space, fine, both in terms of position or sometimes in velocity, acceleration, with minimum deviation. So, that is the most important term. The deviation represents the error, right. So, designing a control law so that the system's actual output YT, that means the actual trajectory, closely follows a time varying reference trajectory RT, such that the tracking error remains small or converges to 0 over time. Okay, that is our objective. So, we want this error to be close to 0 with time. Okay, fine. What are the key aspects? First thing is that time parameterized concept. The trajectory is defined over time. The predefined trajectory which is given, or we can say that predefined means it's the reference trajectory, is defined over time, not as a just a geometric path. It is a time varying concept. Okay. Second thing is that the real time error connection should be there. The controller should constantly adjust inputs, control inputs, to minimize this deviation. Okay. And there should be some assurance of robustness, because there will be disturbances like wind or model uncertainties in the environment. So, the controller which we are going to design for trajectory tracking of drones should be robust also. So, what we see, it is a time parameterized path which the drone needs to follow. The error correction should be done in real time or online, and the third one is that the robustness needed to handle wind gust or kind of disturbance or some model uncertainties. Okay. So, what is trajectory tracking? We understand is that it is tracking the position with time. It will have speed control should be enforced, and the use cases are time sensitive missions, which is very important to understand. Okay. What is the difference with path following? Path following is there is no time dependency. That means a path is given and you have to follow it. So, the specifications are not time parameterized. Okay. Speed control is often ignored in path following. Why it is enforced in trajectory tracking? Because it is time bound, right. So, use cases, surveying, exploration, which are not so much time bound missions. For that we can go for a path following concept, but when it comes to trajectory tracking, then there should be some speed control or velocity control concept inside. Okay. However, this particular lecture might not touch all the aspects, because it is a vast field. We will be highlighting the important topics which will encourage the students to learn more, and we will be giving some reference material which the students can explore. Okay. So, how this particular concept is applied in drone, like trajectory tracking, how it is relevant in drone. Okay. Aerial surveillance and inspection. Okay. When we have to inspect some infrastructure like an important bridge which is connecting two sides of a river and which is very important, then for defense purpose also we might need to inspect the bridge, or some power lines, some pipelines, some important monuments, museum, etc., whatever it may be. Okay. Then security patrols along the predefined routes. When there is a huge gathering of crowds, that time also to check whether all the rules and regulations are being followed, drones can be used for aerial surveillance and inspection. Okay. So, for that accurate navigation over inspection targets at constant speed and altitude will be required. Fine. The second thing is delivery systems. We have seen that the last mile delivery can be planned with the drones. There are lots of videos which you can refer to and understand that what I mean here. Last mile delivery means that when it comes from the final warehouse to the customer. Okay. It requires following a predefined flight path through urban or rural airspace. Predefined, that word is important because that actually gives the reference trajectory, right. Okay. Adherence to air corridors and timing is critical. So, it should be following proper air corridors which are assigned for the delivery system architecture and should not go here and there. So, for that also following proper air corridors in a way where the trajectories will also be predefined should be followed. Okay. And timing is also critical for delivery, right. Another application can be taken as precision agriculture, where the drones are used for spraying or monitoring the crops. Drones must follow rows of crops with fixed altitude and spacing, so that it gets best image to be analyzed later. So, for that there should be a time synchronous coverage patterns for doing the agriculture in a better and more technological way. Okay. There is another very important concept of search and rescue. The systematic scanning of terrain based coverage pattern should be followed here. So, if there is an area which is very important for us to monitor and it is a disaster affected area, maybe flooded area. So, for that if you want to see whether there are survivors, then we should plan a predefined path in such a way that it covers the maximum area possible in the area particular arena, and then the drone also should follow this trajectory as much as possible, so that it can cover the entire area smoothly. Okay. So, the drone must precisely follow time optimized search trajectories, and there should be some integration with sensors to adapt trajectory on the fly. Okay. So, the drone should be integrated with sensor, otherwise even the control loop which we were talking about will not be complete, right. Okay. Then there are formation flying of swarms when they fly in a coordinated trajectories. Applications are like collaborative sensing, defense, sometimes it can be cooperative load transformation as well. It requires real time trajectory tracking with inter drone coordination. So, if not all the drones are following their predefined trajectory, then maintaining the swarm and maintaining their formation will be difficult. So, for that also trajectory tracking is important. Okay. Target tracking and pursuit. So, if a drone is assigned to move a following object, okay, to follow an object, then trajectory tracking ensures that the drone stays at the correct relative position and speed with the object that it is following. Okay. So, these are some kind of representative example scenarios where we know that drone is a very potential solution. However, if the trajectory tracking control is not good enough, then the drone might not serve the purpose, and though it is intended to do some application, we will not get any fruitful result out of that. So, we need proper trajectory tracking, right. Okay. So, I have already briefly told about what is a reference trajectory. We come here to define it formally. A reference trajectory is a time dependent path that defines the desired position, velocity, and sometimes acceleration or orientation of a system at every point in time. Okay. So, that is what it will be given to the drone, and the drone designers or drone control system engineers are expected to generate a control law for which the reference trajectory will be followed by the drone as closely as possible. Okay. So, reference trajectory serves as the target that the tracking controller tries to follow. Please remember this thing, that when we have a trajectory planned for a drone, when there is nothing inside this particular area, like no obstacles are there or not coming on the way from the source to goal location of the drone, then when the drone is covering this path, it should be following this trajectory as soon as possible. If in the initial phase it is kind of oscillating a little bit, that can be that should be handled by the controller, so that finally the steady state error becomes 0 and the drone follows this particular path nicely. Okay. So, the tracking controller should follow one reference trajectory RT, which will be given in terms of x, y and z in 3D space. Okay. The reference trajectory must be feasible for the drone to follow. What does that mean? If the reference trajectory is something which is designed in a very critical way and the drone does not have its capability or actuation support to follow that particular trajectory, then it is not a feasible trajectory, and predefining that kind of reference trajectory for drone is not useful. Okay? Fine. It is often designed using path planning algorithms and then parameterized over time. Okay? Fine. What is tracking error? It is a difference between desired trajectory and the actual trajectory. Okay? It quantifies how well a system is following the reference trajectory. Okay? There are different types of tracking error. One is position tracking error that shows the difference in spatial coordinates, velocity tracking error that shows the difference in desired versus actual velocity. So, desired velocity in that case becomes r, actual velocity becomes y, and what we get is a velocity error. What we get here is a position error, right. Then there can be orientation tracking error also, where there will be differences in yaw, pitch or roll angles. So, these are very important to understand. What we have is a reference trajectory for the drone. What we have to minimize as a control system designer of the drone, we have to minimize is the tracking error. So, the controller should be sufficient to handle the tracking error. That is the main objective. Okay? Fine. So, this particular lecture considers PID controller for trajectory tracking. PID controller is a very useful tracking controller, and will in the results we will show that how PID control is sufficient or can in a very efficient way can help in tracking trajectories, reference trajectories. Okay. So, what was PID? We covered the topic of PID maybe in the last module. So, you remember all these terms. P is for proportional control, I is for integral control, and D is for derivative control. It should work as a controller that automatically adjusts the control input UT, okay, to reduce the error between the desired output and actual output. It should work on, and it should minimize the error, right. How PID control minimizes error? The PID control law is something like this, where the error is multiplied by the proportional gain, then the integral of the error is multiplied by the integral control gain, and derivative of the error is multiplied by derivative control gain, right. So, these are the controller gains, and in the lecture on PID we have seen that tuning Kp, Ki and Kd are very important, right. Okay. So, this is a PID block diagram. What is expected here is that this is the set point where the reference trajectory will come, right. Okay. This is the output Yt. Where the error is being calculated? The error is being calculated here. So, this is plus sign and this is minus sign. So, when we feedback the output like this, then what happens here? We get the error term, which is E equal to R minus Y. Fine. Now, when it comes here, it becomes the error is coming to this all these three blocks. So, here it becomes Kp Et, here it becomes Ki integration of E, okay, and here it becomes okay, and it gets summed up here, right. So, that becomes a controller output ut. What is controller output ut? It is this particular expression, right. This controller output becomes the input to the drone. So, we say that this is a controller output, but a control input to the drone. So, the drone will have its actuators, those are essentially the motors for the propellers. This control input, which is kind of prescribed by the PID controller, this controller will be then effectively applied by the actuators. So, the thrust of the drone will increase in different propellers, the thrust will increase. Sometimes it might be a scenario that some yawing motion is required to follow the trajectory properly, sometimes pitching motions will be required. So, accordingly the motor thrust will be changed, and you have seen in the previous set of lectures of this course that how movement of propellers can generate different level of thrust in different propellers, and how it can achieve the specified or desired motion, right. So, that is what we will be having from the support will be coming from the PID control. Okay. So, proportional control like this reduces rise time, increases overshoot and possibly the peak time, can reduce steady state error a little bit, but can have a little effect also. Okay. Low Kp increases rise time and may increase steady state error, which is a problem, but high Kp also can like increase the overshoot. So, we have there is a what is called a trade off, right. If we increase Kp, there is a problem, if we reduce it too much, then there is a problem. So, what is required is the tuning, right. So, by tuning we can achieve a good balance of speed and stability. Okay. For Ki integral control, it reduces high steady state error with high Ki, can increase overshoot, that is a problem, and because of that increased overshoot and more oscillatory nature in the response, it can destabilize a system. Okay. If it destabilizes lightly damped systems. So, if the damping is proper, then we do not have to, we might not be being very anxious for it. Okay. So, low Ki improves stability, but cannot eliminate steady state error. Then again the problem of trade off comes. Okay. For that, what is required is tuning, and also there is some concept of integral wind up, which I covered in the lecture on PID. For that, some anti wind up controller concept can also be useful, but this is not a scope of this particular lecture. Okay. Now, in derivative control, what is happening? High Kd improves damping. So, from light damped systems, increasing high derivative gain takes it to a sufficiently damped system by improving damping, reduces overshoot, can amplify noise. So, that is a problem, and also can increase control effort if not filtered. Low Kd, again the damping will get less, then the oscillatory response will increase into the system, and then that will lead into longer settling time and more oscillations. Okay. So, tuning for Kd is also required. We have gone through some idea of PID tuning, though not in much details, but we have covered some topics like manual error correction or manual tuning of PID, then Ziegler-Nichols method, and then we have talked about some MATLAB software based PID auto tuning. So, those the students can follow here also when it comes to trajectory tracking. The example which was given in the previous lecture on the generic PID controller was in drone altitude control. Here we will see something else, that is the trajectory control application, sorry, trajectory tracking application. Okay. Why use PID for drones? It is used for its simplicity and ease of implementation. These are mathematically simple concepts, require only basic measurements, that is the error which comes from the sensor, like sensed output, widely supported on embedded systems and flight controllers. Fast real time response if we tune the PID properly. Okay. Reacts quickly to disturbance and deviations, proportional term corrects immediately, derivative term anticipates the trends, and then works on correcting the future errors, and integral term eliminates the steady state error. Predominantly it works on the accumulated error in past. Okay. Why use PID for drones? We have some other points like robust performance in many conditions, can handle moderate model and inaccuracies and external disturbances, stable flight over a wide operating range with proper tuning. Okay. Low computational load, it's simple to implement, perfect for resource constrained flight controllers, no need for matrix inversions or state estimation, what we do for optimal control or nonlinear controllers. These topics, optimal control, nonlinear controllers, we are not touching in this particular lecture series, but those students who are very interested can go on and explore these topics. Okay, then they will understand these concepts like matrix inversions, etc. Okay. PID control easily integrates with feedback sensors like IMU, GPS, optical flow, altimeters, works well with the sensor fusion systems as well with extended Kalman filter. So, we are seeing that PID is a very useful controller for flight control systems. Not only that, it is simple to implement. The only proper care that we have to take is in the tuning of the PID, right? Okay. Fine. Now, another important concept of PID control for trajectory tracking and drone operation will come here, that is called nested control loop architecture. What is that? At this point of time, we have seen that from open loop control, if we go to closed loop control, then there will be one feedback loop, right? That feedback loop, what we have covered in the previous topics was only one single feedback loop. However, for specific applications, we might need more number of control loops. Okay. So, a hierarchical control strategy commonly is used for drone flight controllers. That is why understanding nested control loop is important. It breaks control task into two levels or maybe some more levels depending on the priorities. But what happens is that the outer loop controls generally position or trajectory tracking. The inner loops will take care of the controls like attitude, orientation, stabilization or something like that. Okay. So, why nested? The position and attitude dynamics are coupled, but occur at different time scales. This is very important to understand. Outer loop generally operates slower, controlling translational motion. Okay. But inner loop operates faster, stabilizing orientation to achieve desired forces. Okay. So, we can tell that though we are handling position and attitude dynamics in a coupled way, but since they offer at different time scales, having the same control loop will not be sufficient to control both position and attitude for the drones. Okay. That is why outer loop handles works slowly and handles the translational motion. Inner loop, which can operate faster, works on stabilizing the orientation. Okay. So, what is the final objective? It should ensure stability and tracking accuracy. What is tracking accuracy? It means that the tracking error ET should tend to 0. Okay. Now, for two layer control structure, the outer loop controls the position, translational dynamics using PID. So, how it looks like? It looks like the force FD will be given as the proportional control, integral control and derivative control, and this is the definition of E. Okay. What is RD? RD here is the reference trajectory and this is the actual what we are getting out of it. This is for notation purpose only. Inner loop control controls attitude with roll, pitch and yaw. So, what it will give is the torque, and we get this kind of controller structure where Kp is multiplied with E theta. This is the reference angle and this is the actual which the drone is actually doing. This is the integral control, this is the derivative control. Okay. How it looks like? This is the nested control loop architecture. So, this is the drone with its actuator, sensor and everything. Now, what we have is that from the sensor we get the drone states and pass it from sensor and fusion of sensors tells us about the states, right. Now, in the inner loop control allocation, we will be having this particular thing, altitude and rates. Okay. So, that is for attitude control. Okay. In the outer loop, the same kind of states are coming from the sensors and maybe fusion sensor based methods. These states are coming to the position and maybe velocities also in the outer loop. Okay. So, the outer loop is controlling the position or velocity, and that is why it is at this position. The inner loop is doing attitude control, it is in the inner position. So, from user some desired command will come to the position and velocity controller, then this will give the desired attitude to the attitude controller, then that will generate desired movements and will come to the control allocation block that we will see in the autopilot lecture. So, from that the control input is designed, or what is called the input commands. It will come to the drone, and what we have seen is that with time this particular control loop should bring the error down, right. Both the inner loop and outer loop will work for that. The commands which will be generated will come to the actuator of the drones, that is the propellers. So, sorry, the motors of the propellers. So, it will handle the commands accordingly. So, the drone will move in a desired way. So, that is what the nested control loop is doing here. Okay. Inner loop is for attitude and sometimes rate controls, outer loops are for position and velocity controls, and what we see here is that the outer loop works slowly, inner loop works in a much faster manner. Okay. So, this is just an example of say inner loop position control and sorry, attitude control and outer loop position control. What is happening here? We can see that the inner loop or the inner loop control system is working much faster than the outer loop. How we can tell this? We can tell it because see, the inner loop dynamics is getting settled at around say maybe 1.8 seconds or so, right. However, the output the position control is getting settled, this particular dynamics is getting settled maybe around say 5.5 or something, right. So, we can see that this is getting stabilized much earlier than this particular control, right. So, position control or outer loop controls work in a slow manner compared to the inner loop position attitude control. Okay. So, for this kind of nested control loop, there will be two transfer functions, one for position or outer loop and another for the inner loop for attitude control, right. PID controllers will be wrapped with in the feedback loops. Step responses illustrate that attitude control reacts faster than the position control. So, what we show here, these two figures are with step input, right. Fine. So, what we see here, outer loop smooth but slower tracking of position, right. Inner loop in that way faster to stabilize the orientation. Okay. Fine. So, this is one example of our trajectory tracking of PID, trajectory tracking with PID. So, what is actually expected is that the drone will start from here and will go to the, this is the source location and here is the goal location. Okay. So, ideally the drone should come here in a straight line, right. But since there are some obstacles in between, these black circles what we are seeing are obstacles, just assume that in 3D these are cylindrical obstacles. So, in top view we are just seeing the circle out of that. So, we see start and goal locations. So, for each obstacle there is a safety barrier. Okay. In the control barrier function lecture you have seen that for obstacles what is created is called first there will be the obstacle and then outside there will be some tolerance level or safety tolerance level. So, that is what we are showing. So, in this particular scenario, the desirable thing is that the safety barrier will never be crossed. However, if it crosses, then the near collision area will not be entered by the drone. Okay. So, first you see that this particular dotted trajectories here are the PID trajectories. Okay. And when it is going into the control barrier function motion, that time it is trying to avoid this particular barrier as much as possible. Okay. So, what is happening here? It is a trajectory tracking problem where ideally the drone might be moving from, say, like this, right, the blue line, that should be the trajectory of the drone ideally when the obstacles are not there. Now, when the obstacles are there, we need another concept for obstacle avoidance and safety, and that is given by the CBF, control barrier function. So, when it comes till this point, it detects the obstacle and starts moving or maneuvering so that the obstacle can be avoided safely and it does not go inside the safety barrier or near collision barrier. It is happening, okay, once the obstacle is covered, I would say that it is obstacle 1. Once it is covered, because of trajectory tracking control of PID, the drone tries to come back to its reference trajectory, which I am showing with the blue line. Okay. So, it has a tendency that it will be coming back to the trajectory again, reference trajectory again, right. Now, it observes another obstacle, say obstacle 2. So, it cannot merge on its trajectory tracking, but it has come to as close as possible. Again, it goes into CBF trajectory. Okay. The same thing is happening here, it is again trying to come back to the reference trajectory. So, it is disturbed by another obstacle, so goes away. Finally, when the same thing happens, like the other obstacle 4 is also avoided, then it comes back to the reference trajectory and marches to the goal. Okay. This is a kind of example scenario which shows that how ideally one trajectory tracking should be. Okay. If we are showing it in a 2D representation, visual representation, but the same thing can be happening in 3D as well, where the obstacles should look like cylindrical obstacles. Now, we are seeing it from the top view, that is why we are seeing it as a circle, right. But in urban airspace, just assume that when there are some obstacles, those will be erected from the ground, right, and the drone will face that while crossing. So, it should ideally avoid the obstacle properly and then again come back to its reference trajectory and move on. Okay. So, that is how reference trajectory should work, and we show that how PID can be used to improve the error performance or improve the accuracy of the entire system. Okay. For real world example, we will give the example of PX4 autopilot, which is a kind of open source flight control software, works in a modular and real time fashion. The innermost loop takes care about the angular rate, okay, implemented as a PID on body rates and so. Then there will be another loop which is called the middle loop, it works on the attitude control. So, the first one is the rate control, the second one is the attitude control, and finally, the third one will be position and velocity controller. We know that when this outer loop comes into picture, it actually works in a slow way compared to others, right. So, outer loop will take care of the position and velocity controller. Okay, fine. So, we need to summarize the lecture here. What we covered here is the idea of trajectory tracking. We have gone through the key concepts like reference input, actual output and so. Then we talk about PID. There was a basic recap on PID and then we extend that idea for PID trajectory tracking. We spent a significant amount of time in understanding nested PID control because now at this point of time we know that the same control design for attitude control and position control will not be enough, because though it's a coupled dynamics, they work in different time scales. So for that we need outer loop and inner loop separation. Okay, outer loop takes care of the position control, which is essentially the trajectory tracking control in a positional sense, and then attitude control comes in the inner loop. Then we talk about the example of nested PID control. We show one trajectory simulation result and tell that how trajectory tracking is happening. Okay, so I would suggest that you go through this particular book by Randall Beard, which is a very important resource in this particular lecture, and we are referring it for many modules and many specific lectures. So I recommend you to go through this to understand trajectory tracking in a better way. Okay, thank you, see you in the next lecture.